like, share, subscribe.
Hey y'all, welcome back. Today we are going to learn how to solve a rational inequality. So we're going to solve this almost the exact same way that we solved polynomial inequalities, and that is we will find the roots, we'll draw a little number line, and then we'll pick representatives to decide whether or not the different intervals are positive or negative. But there's one extra little added bonus for these rational inequalities, and that is that the sign can change at one other place other than the zeros. So we still have to find the zeros, but we are also going to have to find where the function is undefined. So basically what that means is this is going to be like extra values that we put on our number line, and we'll probably have more intervals than we would have with the polynomials. So just briefly, when we have a rational expression is going to be one that's like a fraction where both the numerator and denominator are different polynomials. We're going to look at rational functions in a lot more detail in the next unit. We'll learn how to graph them and do all that. But for today, we're just going to be looking at how to solve a rational inequality because the technique is almost exactly the same as solving a polynomial inequality. So like I was saying, for polynomial inequalities, the sign can only change at the x-intercepts or at the roots, which is why we find those, we put those on the number line, and then test to see whether or not the intervals are positive or negative. With a rational inequality, we also have to look to see where the values are undefined and include those as our sort of points on the number line where the sign could potentially change. Now, there's one other thing that we'll have to put on the number line, and when we get to that, I'll show you. But let's work through one example so you can kind of see what I mean. So we're going to find two different things. We're going to find where are the x-intercepts. Okay, so we're going to find the x-intercepts. And we're also going to find what values make the function undefined. So we're going to find the x-intercepts. And those values that make the function undefined could either be holes or vertical asymptotes. We're not going to really get into all that yet. We'll get into that in the next unit, actually. But for now, we'll just say the x values that make the function undefined. So x values that make the function undefined. Or I'll say, maybe not the function because we're dealing with an expression, make the rational expression undefined. Okay, so we got to find those first, then we'll put all of those on the number line, and then we'll pick our representatives and go through that same process that we did for the polynomial inequalities. So first we'll find the x-intercepts. These will occur when the numerator equals 0. Okay, so I'll make a little note here where the numerator equals 0. So what x values make the numerator equal 0? The x values that make the rational expression undefined, well, that will happen whenever the denominator is 0, because you've got to remember you can't divide by 0. So any x value that makes the denominator 0 is going to make the rational expression undefined. So to solve for those, we're going to set the denominator equal to 0. So let's go ahead and find the x-intercepts. And in this particular one, we just have 6x equals 0. So x is going to equal 0. And then the x values that make the rational expression undefined are going to be the ones that make the denominator 0. So x squared minus 25 equals 0. If we add 25 to both sides, we're going to get x squared equals 25. And then we need to take the square root of both sides, and recall that anytime that you take the square root of both sides, you do need to include the plus or minus. So we get plus or minus 5. So these three values, 0, positive 5, negative 5, are going to be the three values that I draw on my number line. Those are going to be the only places that the function will potentially change signs. So I'm going to label those on here. Here's 0. Here's negative 5. And here's 5. And it may be worth, in this particular example, it doesn't make a difference, But in general, it's worth labeling these numbers with whether or not they're equal to 0 or if they're undefined. So like at -5 and +5, this are going to be undefined. And so, maybe I'll actually type that out to make it look a little nicer. Undefined. I'll rotate it. Make this look real good. Okay. And at 5, it's also undefined. And at 0 is when it's 0. Okay, meaning like if I plug in 0 to the function, the whole thing's going to be 0. Now the reason why I'm making this distinction between the numbers making the rational expression undefined versus making them 0 is, let's say this were like greater than or equal to 0, then we would need to know like whether or not we actually want to include the endpoints or not. If it's undefined, we're never going to include that in the solution set. But if it's 0 and this says greater than or equal to 0, then we would want to include that in the solution set. In this particular example, again, it doesn't make a difference because it doesn't say equal to. But as we go through some more examples, we're going to see some where we do have a less than or equal to or a greater than or equal to, so where it would make a difference. And so I just want you to get in the habit of every time you label your graph or your number line here, you make a note on whether or not these numbers are places that make the rational function undefined or make it equal to 0. Now once we have our number line set up, we are going to pick some representatives. So remember, these are numbers that exist inside the intervals. Representatives. Let's see if I can spell today. So the representatives I'm going to pick, if you went through the video, the last couple of videos, you would see that I kind of picked the same numbers over and over again. In this interval between -∞ and -5, I'm going to pick -10. In between -5 and 0, I'm going to pick -1. In between 0 and 5, I'm going to pick 1. And in between 5 and infinity, I'll pick 10. And basically what I need to do here is plug these numbers into x and figure out whether or not the whole thing's positive or negative. So if I plug in -10, I get a negative divided by a positive. So a negative divided by a positive would be negative. So from -∞ to -5, it's negative. From -5 to 0, I'm going to plug in -1. That's going to give me a negative divided by a negative, so that'll be positive. If I plug in 1, I get a positive divided by a negative, so that will be negative. And if I plug in 10, I get a positive divided by a positive, so that's positive. The question here is asking, when is this rational inequality greater than 0? So my answer is going to be in this interval and this interval. So the way I'm going to write that is x is an element of, and I'll have to go grab that element symbol. Again, bear with me. Oh, come on, let's make this red. Yeah, so x is an element of, and I did find it. Hold on one sec. There we go. Let me zoom out so you can actually see the whole number line here. So yeah, we want to say x is an element of, and then list the two sets. So we'll say in between -5 and 0, and both of those will be exclusive because it's not equal to. If it did say equal to, we would include 0 but not include -5. And then union, and then the other set would be from 5, again exclusive, to infinity. And that would be the solution set for this rational inequality. So I guess the key thing to point out here is that you're kind of doing the same thing as what we did when we looked at polynomial inequalities. The only real difference here is that we're also looking to see where it's undefined. So you'll set the numerator equal to 0 and get those x values, and set the denominator equal to 0 and get those x values. You'll put all of those x values, whether they make the numerator or the denominator equal to 0, on this number line. Make a little note to say whether or not it's going to make it 0 or undefined. Pick representatives, one number in each interval to plug in and find out whether or not the function is going to be positive or negative in that interval. And then go back and look to see what the actual question was asking. Is it greater than 0, less than 0, etc. So what we'll go through is a couple of different rational inequalities here of varying difficulty. So I can kind of show you, a few different types of inequalities and what you may encounter on your homework. So let's look at number 2. So quite often, these rational expressions will be written with the polynomials in standard form, and they will not be factored. So you should go into these problems knowing that you're probably going to have to factor first, and just be ready to do that for the majority of these inequalities. So in this case, the numerator here can be factored as x plus 3 times x plus 4. And the denominator can also be factored. Looks like there's a GCF of a 2 that we can factor out, like right up front. So I might do that first. And then I can see that, okay, now this is going to be a little bit easier to factor after getting that GCF of 2 out. Two numbers that multiply to give me 3 and add up to 4 would be 3 and 1. 3 is prime, so it's not like you have a lot of options there. So this can be factored as x plus 3 times x plus 1. Now, you might notice on a problem like this that you've got the same factor in the numerator and the denominator. This is going to have some relevance in our next unit. For right now, all you need to know is that if you have an x value that appears to be an x-intercept and is also making it undefined, the undefined is going to sort of override the x-intercept. So you're actually not going to have a 0 there. So it's sort of like this one's a little bit of a fake out. You don't want to just cancel these out because then you're losing the information about -3 making this function undefined. So don't cancel these out like you might be tempted to. Just leave it the way it is. We'll solve it, and we'll solve both of these equal to 0. And we'll just know that this -3 that we're going to get is actually going to be a place where it's undefined, not where it's 0. So normally, the way you would set this up is you'd say, okay, well, x plus 3 can either equal 0, or x plus 4 can either equal 0. These are going to be the x values that give us the x-intercepts. Okay, when you set the numerator equal to 0. So I'll end up with x equals -3 and x equals -4. Again, we'll come back to this, but this guy right here, this -3, is actually going to be sort of an extraneous solution here because of what happens with the denominator. So with the denominator, we want to find where does it make the function undefined? Okay, what values will make the denominator 0? And so we're going to set this entire expression equal to 0. Our first step would be to just divide both sides by 2 and get rid of that factor. So we can just delete that one. And then so well, I'll just leave it there for just so you're not confused that it just like disappeared or something. But so we'll get x equals -3 and x equals -1. So when you get a number that's like in both of these lists, and this is what I was talking about before, in this case we have -3, then this is going to end up being a place where the function is undefined. There's a little bit more to it that we're not going to talk about today, but in our next unit, when we focus on rational functions like this, we'll go into a little bit more detail on like what's actually happening at that x value. Okay, so this one we're just going to eliminate, and we're going to use it as an undefined. Okay, so at this point we're going to draw our number line. What we're interested in is where is this function positive or 0? Now, if it was just strictly greater than, then not considering this an x-intercept, that wouldn't really matter because you're not going to include the endpoints anyway. But because we're including the endpoints here, we're including where this is equal to 0, we want to make sure not to include -3. So the values here are going to be -4, -3, and -1. Ugh, 4 is like looking like it had a rough time. Okay, so there we go. negative 3, and then we got our negative 1. So basically, we want to plug in some values to see what's going on with this rational function. Is it going to be positive or negative? So it's probably easier to plug it into this, mentally, to just do some mental math with this factored version of the rational inequality. So let's plug in a number like negative 10. So I'm going to pick let's go ahead and just like lay out what our representatives are going to be. So for that first interval between negative infinity and negative 4, I think I'll go with negative 10. Between negative 4 and negative 3, I guess I'll go with negative 3.5. I think might be the way to go there. Between negative 3 and negative 1, I'm going to pick negative 2. And then between negative 1 and infinity, I'm just going to go with 0. So if I plug in negative 10 here, I'm going to get a negative times a negative, so my numerator will be positive. And then in the denominator, I'll get a negative times a negative, so my denominator will be positive. So I've got a positive divided by a positive, so this interval will be positive. Okay? Between negative 4 and negative 3, I'm going to have a negative times a positive, so the numerator will be negative. And then I'll have a negative times a negative, so I've got a positive down here. So hold on, I'm kind of getting lost here. If I plug in negative 3.5, I'm going to have a negative times a positive over, and I'm going to just ignore the 2 because since 2 is positive, that's not really going to affect anything. So I'm going to have a negative times a negative. Okay, so I get a negative divided by a positive is going to be negative. If I plug in negative 2, I'm going to have, that'll be a positive times a positive over a positive times a negative. So we got a positive divided by a negative, so here it is negative. And then finally, if I plug in 0, I'm going to get a positive times a positive over a positive times a positive. I don't need to write all this. It's just going to be positive. All right, so notice here that the sign didn't change at negative 3, and that's because of what's going on with the function. You might, if you're curious, take a look at what this graph looks like in Desmos or in your graphing calculator. And what's going to be kind of interesting is when you look at it, you're not going to see anything too crazy going on at negative 3. In fact, it may look like nothing of interest is happening at negative 3, but the function is undefined there. Okay, so there is something going on there. And again, we'll kind of go into what exactly is happening when you've got a number that makes both the numerator and the denominator 0 in the next unit. So just let that be a little cliffhanger for you. At this point, we can write our solution set because we're trying to find when is this function greater than or equal to 0. So when is it positive and when is it 0? Now, I didn't write down, I guess I should have put down whether or not these are zeros or undefined. So we've got 1, 0. Let's see here, a 0 at negative 4. So we will include negative 4, but we are not going to include negative 3 or negative 1 in our solution set because the function is undefined at both of those places. So let's put that there as well. Okay, so for my solution set, and I'm actually going to just borrow this one real quick. We are going to say that X is an element of the set. Let's see, the first positive is going to be in between negative infinity and negative 4, and we are going to include negative 4 because the inequality is greater than or equal to, and negative 4 is where the function equals 0. And then the next set is going to be in between negative 1 and infinity. And we can't, it's not even so much that we don't want to include negative 1, it's that we can't because there's not even a value there. So we definitely cannot include that in a solution set. And so this would be our solution for this inequality. Okay, so all the values between negative infinity and negative 4, and then all the values after negative 1. Let's look at the next example. Now, this one's going to be a little bit different. Notice that we don't have a 0 on the right-hand side, and so that's something that you're going to have to take care of up front. Okay, you're going to want to get your inequality, if it's a rational inequality, to basically look like a big fraction on one side and then 0 on the other side. Now, this can be a little bit of a pain because it's not easy. Like, we had some of these when we were dealing with polynomial inequalities, and you just sort of combined like terms, but it's not going to be quite as simple with these rational inequalities because you can't just really combine these right away. What you have to do is find a common denominator to combine this with this. And so the common denominator here is just going to be this x plus 2. So effectively what I'm going to do is I'm going to multiply 2, or I guess negative 2, by x plus 2 over x plus 2. Okay, and that will give me my common denominator. So let's see what that's going to look like here. There we go. So we're going to multiply this by x plus 2 over x plus 2. And I'll go ahead and simplify that numerator. 2 times x plus 2 is going to be 2x plus 4. Just kind of clean that up right away. And then now I can combine. So the way you subtract fractions is you just subtract the numerators, assuming the denominators are the same, okay? And you do not modify the denominators. That's kind of the whole reason why we're getting a common denominator, is so we don't have to deal with that. So we get 4 minus 2x minus 4 all over x plus 2 is greater than 0. If you're wondering why I have 2x minus 4 there, it's because when I subtract this fraction, I'm really subtracting each of these terms. So it's almost like using the distributive property here with the minus. So here we go. Notice I have got 4 minus 4. So 4 minus 4 is just going to be 0. So those are just going to cancel each other out. And I'm left with this. And so now I can go through the process of finding the zeros and finding where the x values that make x undefined, do my number line, and then move on. So let's first find the x-intercepts, and then we're going to find where the function is undefined. And it looks like we're not going to have a ton of values here. So, and we don't have to do any factoring or anything. So the tricky part here was just trying to combine these fractions. So we get negative 2x equals 0, so x is equal to 0. No big deal there. And then where it's undefined is going to be where x plus 2 equals 0. So that's going to occur at negative 2. So my number line is going to have 2 numbers on it. It's going to be at 0 and negative 2, so I'm going to have 3 intervals here. And at negative 2, we are undefined. And at 0, we are 0. Now, in this problem, because it's strictly greater than, it doesn't really matter that we differentiate these two important values. But it's good to get in that habit of marking these, just so that in the event that this is an equal to problem, that you remember to include the zeros. So now I'm going to go through, I'm just going to plug in some representatives. So the representatives I'm going to pick here, let's see what we got. A number less than negative 2, I'm going to go with the classic negative 10. You guys know what numbers I usually pick. Negative 1, and I'm going to go with 1. So if I plug in negative 10 here, I'm going to get a positive divided by a negative, so it's going to be negative in that interval. If I plug in negative 1, I'm going to get a positive divided by a positive, so that's going to be positive. If I plug in 1, I'm going to get a negative divided by a positive, so that's negative. Now I'm looking for where the function is strictly less than 0 or greater than 0 here. So my solution set is going to be in between -2 and 0. So I'm going to say x is an element of the set. It's just some value in between -2 and 0. Both of those will be exclusive. So we use the parentheses. And there's our solution set. Okay, let's move on to the next one. All right, so here we've got fractions on both sides. We're going to have to do something very similar to the last one, where we move one of these over to the other side and get 0 all by itself on the right-hand side. But finding the common denominator here is just going to be a tad bit trickier. That should be minus. And the reason being that instead of just multiplying one of the fractions by something, we've got to multiply both of the fractions by something. So like in this previous one, we got away with just, because this had a denominator effectively of 1. So we only had to multiply this by x plus 2 over x plus 2. But if your denominators are different, then you've got to multiply each one. So I'm going to multiply this one by x plus 2 over x plus 2, and I'm going to multiply the second one by x plus 1 over x plus 1. So basically, I'm gonna force these factors in there. So I'm gonna get x plus 2 times x plus 2 on both the top and the bottom. And then over here, I want to multiply by x plus 1. Okay, so now I've got the same two factors on both the numerator and the denominator. Now don't be, when you've got something that looks like this, notice that like this, everything's factored here. Don't go through and FOIL this out and multiply this out if you don't need to. If there's a reason why you would need to, I mean, you can do it at that point. But I would just advise, at least for the denominator here, to just go ahead and leave it in factored form. So now I've got x times x plus 2 minus x times x plus 1 all over x plus 1 times x plus 2. Now, while we want to leave the denominator in factored form, the numerator we need to clean up a little bit because it is not in factored form anymore, okay? So we're going to distribute these, we are going to combine like terms, and then see if we can go ahead and factor it at that point. So the first thing I'm going to do is use the distributive property here and multiply, for instance, this x into the x plus 2, and then this negative x in here. Oh, come on. Okay, so this will be x squared plus 2x minus x squared. Oh, this will actually work out. Pretty nice. Minus x. Now, when I combine my like terms, notice how the x squareds are going to cancel each other out. And then so we've got 2x minus 1x, which is just going to be 1x. So all we're left with is just an x up top. So this actually worked out real nicely. Okay, so at this point, we are going to find my x-intercepts and find the places where the denominator is equal to 0. Okay, so the x-intercepts are going to occur where x is 0 and there's nothing to solve. I mean, that's, there's not even a second step there. So that's kind of nice. And then to find the places where the function is undefined, we're going to have either x plus 1 equals 0 or x plus 2 equals 0. And so the x values where the function is undefined are going to be at -1 and -2. Okay, So now we're ready to go ahead and draw our number line here. I'm going to put 0, so I'll leave a little bit extra room there, -1, -2. So we've got 4 intervals. The representatives I want to pick here are going to be, you know what I'm going to do here, -10. Nothing new here. I like using -10 or plus or minus 10 if that's an option. It just makes it a little bit easier to plug in. And then I've got, let's see, I'll do, I guess, -1.5, -0.05, and then 1. Okay, so let's plug in -10, and I get a negative divided by a positive, so that's going to be negative. If I plug in -1.5, I'm going to have a negative divided by a, let's see what this would be, a negative times a positive would be negative. So again, negative divided by negative is going to be positive. If I plug in -1/2, I get a negative divided by a positive, so that'll be negative. If I plug in 1, I get a positive divided by a positive. So here's all my intervals, and I'm looking to where it is greater than 0, meaning where is it positive, and so I'm going to get 2 intervals here. I'm going to get in between -2 and 1, and from 0 to infinity. And this is a case, since the inequality is strictly greater than, that it doesn't really matter whether or not these important values are undefined or 0. But again, like I've mentioned before, I'm going to go ahead and just label them just to stay in the habit so that I don't forget about it when the time is right. Okay, so let's go ahead and write our solution set for this one. So this will be in between -2 and -1, and that both of those will be exclusive. And then from 0 to infinity. All right, so there's our answer for this one. So I've got one more example for you. This one's just for a little extra practice here. This one's going to kind of put everything together. We're going to have to find a common denominator. We're going to have to do some factoring. So let's just see if we can handle it. So here I'm going to start by subtracting 3 from both sides. And then I will need to find a common denominator. So we have -3 is less than 0. The common denominator here is going to be x plus 7. So I'm going to multiply this guy by x plus 7 over x plus 7. So -3 times x plus 7 over x plus 7. Now I'm going to go ahead and hopefully this won't bother you too much. I'm going to go ahead and distribute that 3 so that when I combine these I can just move straight to combining like terms. So basically I'm going to rewrite this as 3x plus 21. All right, so at this point I'm going to go ahead and combine these fractions, and so I get x squared. It might be just easier to copy and paste at this point. X squared plus 2x plus 19 minus 3x, and again this will be minus 21. This is something we talked about earlier, how when we're subtracting this fraction we do need to subtract every term in that numerator. And so now I'm going to combine my like terms here. So I've got x squared is going to stay there. I've got 2x minus 3x, which would be just minus x. And then I've got 19 minus 21, which is minus 2. Now I'm going to factor the numerator so that I can more easily figure out what the x-intercepts are going to be. So this will be x minus 2 times x plus 1. over x plus 7. So now I can go through and find my x-intercepts. Which are going to be 2 and negative 1. But let's see how I get there. I have x minus 2 times x plus 1 equals 0. Using the zero product property, I can establish that either x can be 2 or x can be negative 1. Now for the places where the function is undefined, or undefined, it's just going to be at negative 7, because if x plus 7 is 0, then x is negative 7. Okay, so let's throw together our number line here, and we're almost done. Oh gosh, the number line is having trouble staying horizontal, okay? All right, so what do we need here? We got a 2, so I'll put 2 over here. We got a negative 1, and we got a negative 7. And negative 7 is going to be the only x value that makes the function undefined. And when x is either negative 1 or 2, the value of the function is 0. Now, since this is strictly less than and not less than or equal to, making this distinction is not really going to do anything for us. But again, and I know I'm getting kind of repetitive here, but in the event that this is like a less than or equal to, you want to know where the zeros are. Okay, so let's start plugging some representatives in here. I think I'm going to go with the tried and true here, negative 10. So yeah, I'm going to use negative 10. I'm going to use a number between negative 7 and negative 1. How about we go with negative 5? And then between negative 1 and 2, I'll go with 0. And then after 2, I'll go with 10. So if I plug in negative 10, I'm going to get a negative times a negative divided by a negative. So it's going to be a positive divided by a negative. So that means in this interval, the function is negative. If I plug in negative 5, I get a negative times a negative. That's going to be positive divided by a positive. So we do have a positive interval here. Between negative 1 and 2, I picked a 0. So we got a negative times a positive. It's going to be negative. And then we have a negative divided by a positive. So our function's negative in that interval. And then finally, if I plug in 10, I get, let's see, 8. Okay, so that's a positive times a positive divided by positive. Everything's positive over here. So if I'm looking to see where this expression is less than 0, okay, that's going to be where the function's negative. So go ahead and grab one of these where I had 2 intervals. Here we go. And so it'll be between negative infinity and negative 7, exclusive because it's not less than or equal to, and we wouldn't include this one anyway because it's undefined. And then the last one will be in between negative 1 and 2. Again, that's going to be inclusive for the same reason, because it's strictly less than. So as you can see, solving these rational inequalities is very similar to solving polynomial inequalities, with the only extra work that you need to worry about is finding where the rational inequality, the rational expression rather, is undefined. There is a little bit more work in trying to get the right-hand side equal to 0, but overall the strategy is extremely similar. So that's it for today. Hope you all enjoyed this, and I'll see you next time.